To increase the intelligence of an AI model, the standard approach has been to make it physically larger. But scaling a monolithic, dense architecture eventually cracks under its own weight, both in physical memory constraints and the sheer cost of computing every parameter for every single word it generates. Inside a standard transformer block, the architecture is relatively simple. You have self-attention, a few normalization steps, and the feed-forward network, or FFN. That FFN holds the vast majority of a model's parameter budget. If you want a larger model, the FFN is the primary bottleneck you have to scale. The industry's solution to this bottleneck is mixture of experts, or MoE. Instead of one massive feed-forward network, you replace it with a collection of n parallel expert networks. The efficiency comes from a mechanism called top-K routing. When a token enters the layer, the router selectively activates just a fraction, say k out of those n experts, and bypasses the rest. Your total capacity scales up with n, but your per-token compute stays flat because you only pay the active computational cost of k. On paper, this decoupling provides cheap capacity scaling, but carrying all those extra parameters in memory is a waste of hardware if the individual experts fail to divide the labor efficiently. Standard top-K mixture of experts suffers from two distinct pathologies. The first is knowledge hybridity. When you have a small number of large experts, each one is forced to process a wide variety of incoming tokens. The expert absorbs a massive, unfocused grab bag of heterogeneous features. The second is knowledge redundancy. Because the architecture does not dedicate any specific expert to handle common baseline features, multiple routed experts end up wasting their internal capacity relearning the exact same common knowledge. To solve this, a 2024 paper from DeepSeek outlines a new architecture called DeepSeek-MoE. They applied two strict structural surgeries to the MoE layer to force true specialization, without increasing the active compute budget by a single floating point operation. Standard MoEs struggle to match the capacity ceiling of an equivalent dense model because these two pathologies prevent efficient parameter use. Discovering a zero-cost structural cure bridges that gap, allowing a sparse model to punch at the weight of a dense one. The first surgery is fine-grained expert segmentation. Instead of running a few large experts, the intermediate dimension of each expert is sliced into smaller, distinct slivers by a factor of m. We have to verify the parameter invariant. You now have m times as many experts, mn, but each one is exactly 1m the size. Multiply them, and your total parameter count remains exactly n. The active compute invariant works the same way. The router now activates mk experts per token instead of k. Since each is a fraction of the size, mk times 1 over m equals k. The active floating point operations remain mathematically identical to the baseline. The payoff is entirely combinatorial. A standard router picking 2 experts out of 16 yields 120 possible combinations. By segmenting by a factor of 4, the router now picks 8 experts out of 64. That expands the available selection space from 120 to over 4 billion combinations. This massive combinatorial space is the theoretical cure for knowledge hybridity. Instead of forcing broad concepts into a single large network, knowledge can fracture into highly focused, non-overlapping slivers. Fine-grained segmentation raises the ceiling on how perfectly a model can divide its knowledge. You buy orders of magnitude in architectural flexibility, and you pay precisely 0 additional flops for it. But segmentation alone only solves hybridity. The routed experts are still completely free to redundantly relearn common features. That requires the second surgery, shared expert isolation. The architecture sets aside a specific number of experts, denoted as KS. These are always on, placed in a deterministic lane that sits completely outside the router's jurisdiction. The specific job of this shared lane is to definitively capture all common knowledge. By firing on every single token unconditionally, it handles the baseline data so the routed experts never have to process it. To afford this shared lane without inflating the compute budget, the architecture shrinks the routed active pool. Instead of activating MK routed experts, it activates MK minus KS. The active size of the shared lane plus the reduced routed lane equals exactly K units of compute. Baking common knowledge directly into the architecture's topology physically isolates the redundant data. The routed experts are forced to specialize, and again, the compute cost remains completely flat. This brings us to the full forward pass. The post-attention state fans out into 3 parallel branches. First, the deterministic shared branch. Second, the softmax router, which calculates affinities across the routed centroids only. and third, the top K routed branch, gated by those affinities. All three then sum together with the residual stream. A softmax router left to its own devices is unstable. It will naturally suffer from routing collapse, where a few experts win the majority of the tokens early in training, receive more updates, and cause the rest to starve. To prevent this, the network applies an expert-level balance loss. It relies on the Shazier trick. You multiply the frozen post-selection token fraction, Fi, by the trainable pre-selection affinity, Pi. The gradient flows only through the trainable pre-selection affinity to force a balanced load. But there is a strict divide between mathematical theory and engineering reality. The flop savings of this sparse routing exist purely on paper, unless you have selective gathered dispatch kernels operating on the GPU. If you use a naive compute-all-then-mask implementation, where every expert runs and you simply zero out the unselected gates at the end, the hardware pays the full dense compute cost. That destroys the entire purpose of the MoE architecture. DeepSeekMoE's zero-cost surgeries require custom CUDA and Triton kernels to physically gather only the selected tokens for each expert. Modern architectural breakthroughs are constrained entirely by silicon-level dispatching, not just the theoretical math. At 2 billion parameters, DeepSeekMoE achieves a 1.808 pile loss, sitting flush against the dense ceiling of a model 16 times larger. At 16 billion, it matches a standard 7B model, using roughly 40% of the training flops. The paper does report a 145 billion parameter scale-up, but that run is explicitly marked as ongoing. It was trained on roughly 1.7 times its parameters in tokens, far below the standard compute optimal ratios, so those numbers are preliminary. There is also a structural boundary here. Across scales, this architecture lags on multiple-choice reasoning tasks like MMLU, which correlates tightly with its heavily constrained attention parameter budget. Because mixture of experts specifically replaces and fattens the feed-forward network, the self-attention mechanism remains untouched. Attention-heavy reasoning tasks structurally cannot benefit from the expanded parameter count, defining a strict limit on what an FFN-centric sparse model can do. The paper claims ultimate expert specialization, but we must separate math from measurement. A 4.4 billion combination space doesn't guarantee diverse routing. Disabling shared experts causes loss to jump catastrophically, proving sensitivity, but not measuring what experts actually learned. To prove true specialization, you have to measure it directly through routing entropy, or by inspecting the weights inside each individual expert. The paper infers specialization through sensitivity, rather than proving it through direct inspection. Despite that epistemological gap, this architecture represents a crucial node in the sparse computing lineage. It moves from Shazier's 2017 sparsely gated LSTM to G-Shard's top 2 routing, to Switch Transformer's top 1, and finally to DeepSeekMoE. Even if ultimate specialization is partially inferred, the rigorous FL-preserving algebra laid out here works. By proving this sparse architecture can run at zero extra cost, this paper wrote the structural playbook powering today's most efficient frontier AI models.